Can get started. It's my pleasure today to introduce our speaker, Jason Hunt. Jason has come all the way down from New York City, where he is a Flatiron Research Fellow at the CCA. Jason obtained his PhD at University College London under the supervision of Jesse Kawata. He then spent a year working at the ESA on Gaia data Gaia data processing and analysis before the first data releases. So he got his hands dirty with data and observation, data and analysis. He then went over to move to Canada to a Dunlap Fellowship at the University of Toronto, where he worked, I think, primarily with Joe Bovey, getting his hands dirty with simulation and theory before moving before moving to New York City, to the CCA, where he's been for the past few years. Next year, Jason's starting a position at the University of Surrey. So congrats on that.
Thanks.
A few words on his work. Jason is, I think, well, as I said, he's gotten his hands dirty on various different aspects of working with Milky Way, formation, evolution, dynamics. I think, at least in my mind, he is currently one of the experts in bridging all of those things and really finding how we connect theory and simulation and observation and getting to a point where our models really match what we see in the data. And without further ado, I will let Jason tell us about our galaxy in motion, ridges, ripples, and spirals in the Milky Way.
Great, thanks so much, Bowman, for that lovely introduction and for all of you for coming to hear me today. As Bowman said, I primarily work on galactic structure and dynamics, primarily in the Milky Way and primarily in the disk. Today I'm going to talk to you about ways that the Milky Way's disk departs from equilibrium and what we can learn from those features. So, stop working now. Yes, okay, cool. Firstly, just a little bit of perspective that the global structure and dynamics of the Milky Way's disk still do remain somewhat unknown. So we have this artist impression here on the right, which is based on some real data, but we don't have this global view of the galaxy. We can't look down on the Milky Way's disk such as we can stare up into the sky for countless other external galaxies. We know we're a barred spiral, but the exact parameters of the bar and the spiral structure have a lot of uncertainty in them. And we already know ways that this picture here on the right, done many years ago at this point, is wrong, even though it still becomes a good illustration for us to talk about the Milky Way. The reason it's hard to get a global picture is because we actually get this view. We are living within inside the disk of the Milky Way. We look out, kind of can't see the forest for the trees type of thing. You see this image on the sky, but it's complicated by a complex selection of effects that are inherent in any survey and complex effects such as dust extinction, which stop you from viewing stars all throughout the galaxy. And so, to some degree, our job is to turn this view that we have here into this view for a global understanding of the Milky Way and what's actually going on in our galaxy. And to do this, we always need more surveys to give us more data, to map more stars and tell us what's going on. We also need good models to help us take advantage of that data and help compensate for the observational biases and selection effects. However, there are also advantages to this view of our position within the Milky Way. It's the only galaxy where we really have a 3D laboratory with positions and motions for billions of stars. We can kind of see galactic dynamics happening up close, not over timescales, because we have this single snapshot frozen in time, but in like a fine resolution, whereas we look out into the real universe, we only see galaxies kind of as a whole. So to give us more data, this is the European Space Agency's Gaia mission, that I said I worked for briefly, launched back in December 2013, ESA's cornerstone mission, and the tagline was to map 1 billion stars in the galaxy. It was supposed to cost $1 billion, so every dollar you spent was to give you one star's worth of information. However, in the end, it's mapped about 1.8 billion stars at this point. It's doing way better than expected and somehow stayed on budget. It's primarily an astrometric mission, so it gives us positions on the sky, parallaxes, proper motions. So it's very well complemented by other ground-based surveys that give us spectroscopic information, such as more radial velocities or elemental abundances, such as from the SDSS missions, but many others. And yeah, just as a short summary of what Gaia has given us up until this point, 1.8 billion stars positions on the sky, then 1.5 billion, 1.5 billion for the astrometry and photometry. So this is parallaxes, proper motions, brightness and color. then you drop down to a couple of 100 million low resolution spectra and astrophysical parameters, temperature, mass, age, color, metallicity, but they're not particularly precisely measured, but we do have a broad sample. And then down to about 33 million radial velocities, which complete the 6-dimensional phase-based information of position and velocity. So that's the sample I'm mostly going to talk about today. If you're not interested at all in galactic stuff, Gaia also measures a lot of binary star systems. It measures a lot of asteroids in the solar system. And it can find, I believe, Jupiter mass planets to dissect, I think was the was where they get to. But yeah, this is the current state of the data set. We had data release 3 last June. And for me, as a galactic dynamicist, QA survey scientist, the most exciting thing has been that we've started to be able to make large-scale maps across the Milky Way's disk, not so much in terms of structure, because extinction effects really make it hard to calculate stellar densities over large distances. But if you're looking down on the plane here, so this is putting a little ring roughly corresponding to the area of these plots, you can see this is a map of mean radial velocity, motion of stars towards and away from the galactic center. This is mean rotation velocity, the stars moving around the galaxy, and these are their dispersions. And you can start to see a large scale structure here. The radial velocity stars moving inwards, blue stars moving outwards. And I'm not going to go into too much detail, but basically what you see here is everything is not smooth and stable. If we lived in a perfectly axisymmetric disk in equilibrium, these would be effectively 0. But no, there's lots going on here. This is not a surprise to us, as we've always known we've lived in a bad, well, not always. We know we live in a bad spiral galaxy. This should be here. But Gaia's really helped us start to push these maps outwards and see what's going on. This is interesting, not just for like galactic cartography, but these velocity fields can inform us on what's actually happening in the galaxy and the dynamics that underlie them. And I said Gaia is well complemented by spectroscopic surveys by combining Gaia with Apogee and a neural network work from Henry Lung and others, and show that you can make these kinematic maps over much larger distances. And you see now the kinematic imprint of the galactic bar pop up in the middle of this plot. So this is azimuthal velocity. This is radial velocity. You see the quadrupole, which is a known feature of a galactic bar. And similarly, Christina Eilers, myself, using a different technique, map this large feature of radial velocity out here, which looks roughly like a spiral pattern, which could correspond to one of the Milky Way's outer spiral arms. Still a lot of debate on that. But we are starting to get to a stage where we can map large-scale kinematic features across the galactic disk. And there's one final one of these, which I really like. This is that same selection from Christina Eilers, now updated to color code by metallicity, this is iron over iron abundance. And you see the metallicity gradient very clearly as you go out to the disk. And each of these little arrows are showing the motion of those stars. You can see clearly the galactic rotation, but also in the middle, you can see flattening these arrows into the galactic bar region. So yeah, we're just getting to the stage where this is doable and exciting and lots of things for us to learn. The other thing that Gaia highlighted in DR2 was ridges and ripples in galactocentric radius versus azimuthal velocity. So now you're looking at R, so this is distance to the galactic center along the bottom of these axes, versus V phi, so the rotation around the galaxy. And we see ridges or ripples are prevalent in this space. This is 2 papers that were submitted the same day, a couple of days after DR2. They're showing them both, but they find basically the same structure, these ridges in the galactic disk. We have, we know ways to form these. This is the first showing over large distances, but they're actually extensions of the long known moving groups in the solar neighborhood were found by Hall and Hagen back in the late 50s. So you have here Sirius, Heronices, Hyades, Pleiades, and the height of these streams, and the local velocity structure of the disk, radial velocity versus azimuthal velocity. And these correspond. Sirius is this big ridge here, which stretches across several kiloparsecs. Hyades, Pleiades kind of blur together, but they're this ridge here. These two are Hercules, and you can see the hint of this thing that's actually called the hat is this big ridge up here. So originally, Hagen thought they might be dissolving clusters, and people discussed this for a while. There were many other reasons that's not the case, but you can now see just very cleanly that these are large-scale dynamical features which stretch across the disk. The other thing that was found by Teresa and Toya in that same paper was striking spiral pattern in ZVZ or ZVZ, depending on where you're from. And this is so Z is position above and below the disk plane. VZ is motion up and down. So this is taking a local volume and plotting vertical position versus vertical motion. And you see a spiral pattern pop out just about in the number density of stars. It's kind of faint. Radial velocity, you have a hint of it as well, still not very clear. But in azimuthal velocity, it really pops out and you get this striking spiral or snail-shaped pattern in the position and motion of stars up and below the disk plane. And this is some indication that there has been some vertical perturbation to our galactic disk and it is phase mixing back towards equilibrium. And we see all these features in simulations. We see large-scale bar spiral arm patterns, but also the ridges in the radial position versus azimuthal velocity, and we see the snail spirals in the vertical position of motion. And it's important to look at these in simulations because they help us do two things. Firstly, they let us look across the global state of the disk to get around the selection effects from dust extinction and survey science, etc. You can see how they propagate across the galaxy. But they also let us explore how they form and evolve with time. So you're getting into another dimension you just can't do in the Milky Way. However, simulations are of course not ground truth, and you must always come back and data to see if what you're doing does appear to be sensible. And just in brief, these ridges can be made by bars. We know bar resonances leave the imprint in this space. The different, this is, RV phi in density from a barred n-body model from Francesco Frangutti, and the ridges also pop out in radial velocity. So you can make them with bar resonances. I'm not going to talk about that too much today. You can also make them with spiral arms, whether you prefer density wave spirals or transient winding material arms. They both leave ridges in this space, basically any departure from equilibrium in this distance. There's another image of the Gaia data from me combined with apogee. And as one of my models with spiral arms, you see the same ridge features appear. And if you have just a bar and a smooth disk, so this is a test particle model run by Matthew Bubb, who was an undergrad when he worked with me, now grad student in Perimeter. An isolated disk, when we grow the bar here, so you start from this smooth distribution. This is what the galaxy would look like if absolutely nothing was going on. Oops. And then you grow a bar smoothly and slowly, and you'll start to see this red-blue pattern appear in the middle. So this is known as the outer, well, it's caused by the outer limb line resonance of the galactic bar. And if you know things such as your galactic potential, the rotation curve, you can use these features to measure the pattern speed of the bar, because that affects where this falls in this place, and the amplitude of the bar, because it affects how strong this feature is. If you have just a bar and nothing else going on, you can do this. However, if we then turn on some spiral structure, you see this space actually then becomes quite messy. There's a lot going on. So a lot of these red-blue features, a lot of these ridges in this plane. And so we know, because this is a model, we have complete information, that this ridge gap here is the one that corresponds to the bar resonance. So you could measure it. However, if you come just looking at this, yes, go ahead.
Can you say a few more words about the simulation? So you model the potential, and then you have ways to mimic the presence of the spiral arms, and then these are really test particles.
Yes, that's it. This is a relatively simple simulation. So it's a test particle disk just sampling from the equilibrium potential. We impose a bar potential in the middle, which is it's like a modifier that increases the density of the inner disk along the bar axis and decreases it off it. And we grow it slowly in amplitude and length over time to not just shock the test particle distribution. Then we turn on spiral arms, which are also grown slowly in the same way. This particular instance has transient spirals that are extending from the end of the rotating bar that grow and decay repeatedly a couple of times. You get the same ridges if you have a variety of density wave spirals as well, but the exact patterns will be different. But the broad combination of bars and spirals leads to a messy set of ridges in the space.
Sorry if I missed this, but the particles, they talk to each other or just really test particles?
Not in this instance. So I showed before, this model from Francesco Frangutti is live self-gravitating, they all interact. This one is a toy model to show when everything is clean with just the bar without the self-gravity. But yeah, we'll come back to self-gravitating models later. And just to add further, these ridges in this space can also be made by the impact of satellites on the galactic disk. This is another live n-body model from Sherman Report. He has another projection of the Gaia data on the left, and these ridges are here. And when he drops a dwarf galaxy into a n-body disk, you make the same ridges. However, in this instance, you're really making spiral arms with the impact of the galaxy, which then make ridges. So how you disentangle it is a bit more of a gray area. But the advantage of the satellite impact model is that it also makes these phase spirals in Z, BZ, which don't necessarily arise from the other models. We have here again the Gaia data from Teresa and Toya on the top, the spiral in density, radial velocity, and azimuthal velocity. In Shervin's model, you can only see it in azimuthal velocity because the resolution of the model is not good enough to sample a local volume and recover the spiral in the density space. You just don't see it. However, this is from 2017, and with more advanced computer hardware and like more better developed n-body codes, you can now get up to much higher resolution. So Shervin had about 5 million particles in the disk, I think 50 million overall. And so I've run this new model, 1 billion particles overall, 200 million in the disk, which starts to give you the resolution necessary to resolve features over local phase space. So this is a self-propagating model. It's still to some extent a toy because the disk is very warm, it's very stable. It's not meant to perfectly reproduce the Milky Way. This is supposed to be a laboratory for investigating merger dynamics. You have here on the top left, surface density of the disk. This will be the radial velocity, motion of stars inwards and outwards. This will be the mean height above and below the disk plane. This will be the mean motion of stars up and down. And this is the edge-on view of just the galactic disk and density, and you will see just the satellite in this bottom panel when it comes through. Initial conditions taken from Widram Dubinsky's 2005 paper, where they set up this very stable disk. For the dynamicist in the room, it has a high tumor cube parameter, and the disk direction is light. So yeah, it's not particularly Milky Way realistic, but there you see the satellite go by. You generate a lot of spiral structure in the density. You generate a lot of coherent motion in the radial velocities, the vertical position and motion. And as the satellite comes through again, you induce structure on top of structure. You start to pull material up off the edge of the galaxy, creating these feathers that we see in the outer disk. And just as the satellite gets further and further in, you get more and more dynamics. And then at the end, this bar starts to fall in the middle of the galaxy. So plenty of people can run these kind of n-body satellite merger models. The thing that makes this interesting is the local phase space resolution lets you start to investigate the spirals. And to be clear, this is not the Milky Way Sagittarius system. But we're still going to choose a present-day snapshot and look at it and compare to the Gaia data. And we choose the moment when the dwarf is about to punch up through the far side of the galaxy from our chosen solar observer to put it in a similar place as the Sagittarius dwarf today. However, the dwarf is more massive and the disk is too hot. We shouldn't expect to perfectly reproduce the Milky Way system. We also choose this snapshot because it's before a bar has formed in this galaxy, so that we don't confuse future kinematics that we're looking at to arise from the bar. But of course, the Milky Way would have them. And interestingly enough, satellite impact makes all the disequilibria features that we see in the disk. Again, it shouldn't perfectly reproduce, but this is the Gaia data. This is the simulation. You have all these ridges in galactic radius versus azimuthal velocity. We have this phase spiral in Z versus VZ. It's the Gaia data. Simulation is not quite as well wound, doesn't match morphologically, but again, it's not the same system. It's qualitatively right. But the thing that was interesting and we totally didn't expect was you actually do a really good reproduction of the local solar neighborhood classical moving groups. This in Gaia, you have again Hercules, Hyades, Pleiades, Berenices, Sirius in this like trimodal main mode, and the Hercules at the bottom, and the faint hat feature on the top. We actually got all those out without trying to. We have the trimodal main part of velocity distribution with the correct vertex deviation. We have our separate Hercules moving group, and we have our hat on the top. I'm definitely not claiming that we have found the origin of the solar neighborhood moving groups. That's definitely not true. This is just a complete coincidence. However, my point is that if you were to look at this distribution, people frequently use Hercules or the hat to measure parameters of the bar, both strength and pattern speed. If you made that measurement from this simulation, you would be measuring essentially nothing because there is no bar in this model. You just happen to reproduce the kinematics which are often associated with. And with that, I will leave the radial and planar stuff mostly behind and start to focus on the phase spiral. So again, in this model, we can select a little local volume. This is going to be our solar neighborhood in the simulation. It's on the far side of where the satellite is today, which is the green dot. We make this nice one-armed phase spiral, similar to we see on the Gaia data. Not as finely resolved because even 1 billion particles is still far short of the real galaxy. And I'll do a brief digression on how and why these spirals form if you're not a galactic dynamicist. It's all to do with frequencies and epicycles. So you have this image from Wilmot-Trick's PhD thesis. On a galactic orbit, there's an orbital track of stars that are fairly close to being circular, but not quite. So you have this orange orbit here, which is perfectly circular. Blue orbit, which has a little bit of radial eccentricity. It crosses multiple radii as it goes around the galaxy, and the green one, which has a bit more radial eccentricity. We are interested in the vertical direction. So here, this orange orbit, it may be circular in the radial direction, but it has vertical extent. It oscillates between about 100 parsecs up and down. And the blue one has both radial and vertical eccentricity. The green one has a lot of radial, but no vertical eccentricity. And so if you map these orbits onto the ZVZ plane that I've been showing, the green orbit, the one that has no vertical eccentricity, would just be a point in the middle. The orange one, which has a bit more vertical eccentricity, would be somewhere in the middle of this. And the blue orbit, which has higher vertical eccentricity, will orbit around the outside. And if you're not a galactic dynamicist, you can roughly call actions, angles, and frequencies. So the phase of where a star is around its orbit. The action is the area. So the further it is from the center, the more area it sweeps out, the higher the action. And then the frequency is how it would rotate around this orbit. And stars in the middle will have much higher frequencies. They complete their epicycles much quicker than stars towards the edge.
So, sorry,
Yes.
would I get the rough features of the spiral if I only worry about that? Can I get that in a shading box? Or I understand what part of the global dynamics actually are critical to get this.
People have done it in the sharing box. All you need to make the phase spiral is some perturbation away from equilibrium, and it will wind up into a spiral. So reproducing the correct spiral of the Milky Way is much more complicated than that, but reproducing any spiral, it's a pretty natural consequence of any perturbation away from equilibrium in space. So I have a little illustration of that. For example, if everything is in equilibrium, this distribution is not quite circular here, but close enough. It doesn't matter that the frequencies are different. They will still look like a smooth, uniform sphere until you distort it. If you pull everything away from the center of the potential, then the stuff in the middle goes around this space faster than the stuff at the end, and you smear it out into a spiral. And that's really what's going on here as like a basic illustration. We have this nice animation from Adrian Price Whalen that if you have essentially a full shift of stars off from the center, they wind around like this, just because the frequencies of stars in this, the vertical frequency of stars in the middle of this space are higher than the ones at the edge. So making any kind of phase spiral is pretty straightforward and should be a natural consequence of any vertical disequilibria. Working out exactly what happens to the Gaia ones is much more complicated, and that's what I'll be talking about. Yeah, and so over time, these wrap into these phase spirals. And just as an aside here, you will notice as I show plots from different groups, some people put Z on the x-axis and DZ on the y-axis, and some groups like VZ on the x-axis and Z on the y-axis, and they feel very strongly about this. Personally, I don't really mind. But the point to watch out for is that in this instance, you'll get a spiral that's moving clockwise, and in this instance, you'll get a spiral that's moving anti-clockwise. They're all the same. They're all trailing spirals. They're all phase mixing in the same direction. Whether you see clockwise or anti-clockwise is just the choice of the coordinate system that people are using, or not even coordinate system, projection. And the reason we're interested in these spirals is because they contain information about our galaxy. So it's a study of 4 papers from Axel Widmark showing that you can use the shape of the spiral to constrain the local galactic potential, because you know the orbital tracks in that space. You know how stars should move, and if they're shearing out into a spiral, you can kind of back out the potential information. I'm not going to talk in detail about this project. I encourage you to look at its papers if you're interested, but this is an illustration of the paper where he tested on the simulation I just showed you. And even from this very almost not a spiral that you can perhaps just about see on the right, he gets effectively the correctly recovered vertical potential in a local area. And then if you know the potential, you can theoretically unwind the spiral and get information about the originating perturbation, such as how long ago it was. So we have this pilot study from grad student Elise Direct-Ford, where from this very clean, nice, simple spiral, we can, in a known potential, we can unwind it back and get an estimate of the time when we first perturbed that distribution of stars, and she recovers it very well. I think it's 844 million years, and the truth is 850. However, in practice, it's not quite this simple. Firstly, the disk has its own self-gravity. If you distort a bunch of stars away from the midplane, some of the potential comes with that because they are creating the gravitational field. Secondly, you probably aren't starting from a perfectly smooth distribution. You will have had older interactions, whether it's another satellite perturbation or anything else going on. So you don't start from a uniform field, so your spirals can be kind of lumpy. Thirdly, we have the recent paper from your own Scott Tremaine showing that giant molecular clouds can cause diffusion in the action, actually wipe these spirals out earlier than if they were left to wind up by themselves. Fourthly, you can have multiple perturbations going on at the same time. I'll talk about this paper a bit later. You can have multiple spiral patterns interfering with each other. And then finally, even if none of those things are the case, and you have a nice clean single perturbation and no GMCs and no previous interactions and no multiple perturbations, you still actually are left with a superposition of phase spirals in a local area. And that's because a local volume, so this is again the Gaia now DR3 data you see in the density already pops out within 1 kiloparsec of the sun. This actually contains stars on many different orbits. We have a population that are close to circular, which will dominate. You also have many stars that are visiting the solar neighborhood from the outer galaxy on the inner part of their radial epicycles. Many stars with lower angular momenta that are visiting us from the inner galaxy on the outwards part of their epicycles. And if you split this main local phase spiral by a function of angular momenta, you end up seeing different phase spirals. So in this is left to right, inner to outer galaxy split by angular momenta. You may not be able to tell much difference between panels directly next to each other in the middle. If you look from the left to the right, you end up with quite different morphology. This is actually a feature, not a bug, because it lets us probe the interaction from different perspectives. So if you imagine today on the right, you have this local group of stars. If you track where all of those were 1 orbit ago or 2 orbits ago, they can end up spread out far across the disk. If happened to be some kind of perturbation 2 orbits ago, you'll be carrying different information depending on what that perturbation was from a different dynamical perspective back into the solar neighborhood for us to use today. So as an example of that, so the model from Suraj Gandhi, a Columbia grad student, test particle model doing the same thing. So this is looking down the face of the disk, selecting a local solar neighborhood and splitting it by angular momenta. You see these spirals have clearly different morphologies, tighter wound from stars with low angular momenta, less wound stars with high angular momenta. The other thing to note, this one on the right, it's a little hard to tell on the color bar. This is the strongest amplitude of the spiral, and these two are the weakest, and these two are somewhere in the middle. And then because it's simulation, we can trace back where they were in the past. And we see that this group on the right, the high angular momenta stuff, was indeed further out in the disk. But it's also pretty much exactly where a satellite passed through the galaxy. So that's where this big red blob here, and this red group was almost perfectly on top of it. Conversely, the green and orange groups are actually at that point on the far side of the galaxy. They had less amplitude in the perturbation, and they result in a less strong phase spiral. And the purple and blue ones are somewhere in the middle, a bit closer. So that all kind of makes sense. And this is a nice illustration of how, even from a small volume today, you can potentially get information about a perturbation spread far across the disk. The other things, as well as splitting by angular momenta, you can also split by saying the dynamicist azimuthal phase angle, the conjugate angle to the azimuthal action. For the non-dynamicists, this is saying splitting stars by whether they spend more time ahead or behind the sun on its orbit. So if you do that same split, again, panels next to each other look very similar, but going all the way from the left to the right, you see clearly different morphology. So there's also that dimension that you can split by, and you can do them in the simulation as illustrations. So we're going back to my main big self-consistent merger simulation. 1 kiloparsec, you get your clean phase spiral. If you go to further distances, it all blurs together more. But even within 1 kiloparsec, you can split it by an angular momenta and azimuthal phase angle and get out spirals of different morphology. However, now we are starting to run into the particle noise from the simulation. Even 1 billion particles is still not enough. However, if you split by these at the same time, you can start to make these 2D maps of how the spiral varies across, it's not quite physical space, it's more orbit space, but even from a local 1 kiloparsec volume, you can sample phase spirals that have guiding radii of about 4.4 kiloparsecs or a phase range of about 40 degrees, which is much further than you can get when looking in physical space because of selection effects. Again, for dynamicists, this induces a radial action, that phase dependence discussed in the paper. I won't go into it today. And all of these spirals in this grid that have significantly different morphology in different areas are all contained within this one phase spiral. in this one region here at the simulation. However, the advantage of the simulation is that we are not constrained to the local volume. We don't have selecting effects. We can look everywhere. And so you can do this. So what you have now on the right, each of these little tiny spirals is the phase spiral that you'd get if you took a 1 kiloparsec box in that area of the galaxy. So this is a 30 by 30 grid of 1 kiloparsec box sizes and the spiral that you'd see in all of them. Now, this is quite a busy plot. Also, I don't know how well they come out for people at the back, but the 3 things to take away here. One is these phase spirals are ubiquitous. The whole galaxy has been perturbed. We're not living in some special area by the sun that just happens to have one. They're probably quite common if you've had any kind of interaction history. Secondly, phase spirals that are near each other look very similar. You may have to take their word for that if you can't see them, but phase spirals over the opposite side of the galaxy look very different, although similar to each other in their groups. And thirdly, that if you kind of squint a little bit, the whole thing looks like one big spiral.
Why?
Why for the big spiral? Yeah, so actually this is a simpler case. So this is Z versus VZ. So when you're having, say, the entire distribution dragged away from the midplane, you're going to leave white space behind where there are no stars. So in this image, it's the offset of the spirals from the center in a coordinated fashion. So if you look at this map compared to a global map of vertical position and velocity, you see the same kind of structure, because the big spiral is just offset from the central point of that ZVZ panel. It's departure from like the equilibrium state.
Out of curiosity, and what would you get if you were to consider the entire galaxy as one body?
That's an interesting question. I think you'd get something closer. I think you'd still see some kind of structure, but it will be very messy because you'd have a large amount of stuff superimposed on top of each other. I don't think it would go back to just being a uniform ball, but I haven't done that test, I'm not sure. And then because I can see everyone looking at this and deciding there's really not enough information in this plot and that you'd like more panels. I've added 750,000 more panels in the form of time evolution, because that's the other thing that these simulations can do. So this is that same grid starting from the beginning. Nothing's going on. It's very smooth. It's very stable. It's lags behind my laptop, so I should watch this one. This is what would happen if there's like absolutely no vertical perturbation in your disk. Here's when the satellite goes through, you see the entire plane be distorted as spirals are pulled away from the midplane, or stars are pulled away from the midplane, and then you see them start to wind up into these phase spirals. You see them propagate out across the disk. That's the second interaction then. I think the Zoom's struggling with it a little bit. If you want the smooth version, I can pass the link later. But you see over time, more and more spirals are induced on top of the existing spirals. Everything gets kind of messy, but they become ubiquitous across the whole galaxy. I'm going to let that run through once more because I particularly like this, and I have a couple of things to point out. So,
what is the point of this exercise? I mean, given that we live in a stable position in the galaxy, and I mean, I don't think there is any hope of visiting other places.
You'll certainly never be able to make this either in terms of the entire galaxy or through time. But I would argue that's entirely the point, because we, in our local volume, will only have one little sample, or eventually we'll get a little bit further, we'll have some small region to sample. But seeing the way that they change or the properties of them in a local volume and actually relating that back to an origin is hard. And so having simulations where you can track how these things evolve over time and how they do change spatially becomes important. This particular animation is mainly just for fun. It's quite hard to interpret, but the individual panels and the like statistics you can do on the spirals over time, I think, are quite informative, because you absolutely cannot do this with the real data. And to freeze on a couple of points to show what we did learn from this ridiculous animation. There you go. After the first passage, you get this ring of phase spirals, which are all very regular, and they're also all two-armed. So there's this little band in, not quite the fully outer disk, but further out from the sun, and all very regular, look very similar. And then later on, towards the present day snapshot that we chose, then you end up with these one-armed phase spirals close up to the solar radius, like we see in the actual data, and the outer galaxy has become a big mess. And we know why this is. It's owing to the nature of the interaction. That first passage is very impulsive, it's very fast, it's impulsive. is the satellite goes by the edge of the disk really rapidly, faster than the vertical oscillation period of the stars. They don't really have a chance to go anywhere. Basically just inject energy into the space, and it induces what's called a breathing mode. The stars above in the disk are going oscillating up and down like that with respect to each other. And then the second passage and later passages again, slower, they're more extended. They like sweep under the disk, take a few 100 million years, and they induce something that's called a bending mode, where the stars are moving down and up like that together.
Can I ask?
Yeah.
So what would be the, if you were to have the ability to have consider the gas in the galaxy, how would this play with the energy dissipation when you?
Yeah, it's a good question. At the moment, we haven't been able to include gas primarily just because of resolution questions. If you want to resolve lots of local phase spirals with hydro simulations, it's difficult. But two ways. One, I think the thinner gas potential will give you like the extra little thin layer of the potential will change slightly the inner regions of the phase spiral and how they mix. But also stuff like the giant molecular clouds and other real physics that we don't have incorporated into these M bodies will do stuff like Spectrum's paper shows, do diffusion and help wipe these out sooner, I think. So the behavior won't be exactly the same, but I think it should be qualitatively the same. But like we're working towards that. I have a hydro simulation running at the moment, which has 100 million particles in the disk, so we should be able to compare, but it's taking a long time, as it should do. So I might be able to give you a more satisfying answer next year, but not right now.
Is this a high tumor Q galaxy?
Yeah, this is very hot. We have run the same models and mergers, etc., with reasonable Milky Way like disk galaxies, and you see qualitatively the same structure. The reason I show this one is because this is the only thing that's going on, the satellite, whereas other galaxies, as I'll talk about later, when you have a bar and spiral arms that generate breathing modes self-consistently by internal dynamics, also make phase spirals. And that's what I'm talking about when I say multiple perturbations can perhaps interfere with each other. So this is a clean laboratory for looking at one origin, but it's not as realistically Milky Way-like as other ones.
The response, this response probably depends on tumor Q.
It does, and you can see it in the, I jump all the way back to, yeah, this one. You can see from that first impact, as you have the spiral arms induced and they propagate outwards, it's very clean, nothing's collapsing under itself, safe gravity. The same is true of the vertical position of motion until you get later on. So yeah, it will change things. But like qualitatively, the grids of spirals you can get in more realistic Milky Way galaxies, they still show the same behavior. So it depends on exactly what question you want to look at.
I guess I'm sort of telling on that question about addition of gas, because addition of gas typically tends to lower tumor Q. So that would amplify these effects, I guess.
Yeah, that's right. Gas should be included. It would be more realistic. It's just computationally difficult at the moment. And yeah, for the breathing and bending modes, just again going back to this cartoon of how they form. Bending mode is essentially dragging stuff down. The breathing mode is essentially stretching it out, and then they wind up into 1 or 2 armed phase spirals as they are departing from equilibrium. So that's effectively how that happens. There's some nice papers by Urup and Bannock that show this in more mathematical detail. This is just a way cartoon. But why am I talking about that? Because the Gaia spiral that I've shown you so far is one-armed. This is the spiral in the local Gaia volume. Well, this is also the spiral in the local simulation volume that we chose to be the solar neighborhood, and generally for the radius of the sun, regardless of the chosen neighborhood. And so in 2021, I had a version of this talk that ended predicting, because actually the simulation shows the relics of these 2-armed breathing spirals in the outer disk. They're messier, but they are still there. You can just about see them. And so I predicted that perhaps you would be able to find relics of these old breathing spirals further out in the real Milky Way once we had data that goes that far. I'm no longer sure of that, because after Scott's paper about the diffusion, and they should probably wipe them out long before they get to this point. But in any case, in this case, we can't check. They're still far beyond the observable volume. However, in Gaia DR3, we did actually discover these 2-armed phase spirals. However, they're in the inner disk, which was the opposite of where I was looking for them. However, if you make this map from, again, splitting in the actions and angles, so it's not a true physical map, but it's splitting by angular momentum or guiding radius and the azimuthal phase angle, you see essentially an overlap between two-armed spirals caused by breathing mode and one-armed spirals caused by bending mode. The blue box, breathing mode in the inner disk. And we could actually have predicted this because there are older papers by E.G. Mary Williams or Aaron Krollo that say detections of a breathing mode a little bit further in the galaxy. And in the solar neighborhood, the spiral that we'd seen before is one-armed and going out as far as we can see. This is actually still well short of the prediction I showed you on the previous page, which will be somewhere off the right of the TV screen. We still are nowhere close to it. So it could be out there, but I'm not confident. But it is interesting that we see even in the local volume, the two different types of phase spiral. And the picture I just gave you doesn't work for this. So I said that when you have a really fast interaction, if the satellite goes by faster than the vertical frequency of stars, that it will induce a breathing mode. If it's slower, it will induce a bending mode. Well, you can't be faster than the stars in the inner galaxy, which oscillate up and down much quicker than the stars in the outer galaxy, which is slower. So this little kind of toy hand-wavy model doesn't work. So we need another mechanism, or our understanding of it is just completely wrong in the first place. However, luckily there is another option which works quite well. So this is now a much more realistic Milky Way-like disk galaxy, showing you a two-armed phase spiral in the inner disk that arises self-consistently from either the bar or spiral structure. We still need to do more work to determine exactly what is the formal origin, but this galaxy just forms a bar and it forms spiral arms by itself. It forms a breathing mode in the inner disk. Other works, Giacomo Manari or Victor De Battista have talked about transient spiral structure creating breathing modes, so that's not entirely a surprise. But in the outer disk, there's nothing. We see no phase spirals at all. Fortunately, I don't have the movie for this one. It wasn't run to the same resolution. We should go back and resimulate it now that we know that it's interesting. However, if you take that same galaxy that has two-armed phase spirals in the inner volume, nothing in the outskirts, and then you throw a satellite at that one, you actually reproduce what you see in the Gaia data quite well. You retain the two-armed breathing mode spirals in the inner disk, caused by Gaia spiral arms, and now you have one-armed phase spirals in the outer disk, caused by the satellite. Again, we totally do not match quantitatively the phase spiral that we see in the Gaia data, not as tightly wrapped, the amplitude's wrong, but qualitatively, you can reproduce the split quite nicely by a combination of internally to externally induced vertical disequilibrium. So I suggest that that is what we are seeing here in the real Gaia data. The two-armed phase spirals, the breathing mode from the inner galaxy being generated self-consistently by Milky Way symmetric structure, and the one-armed phase spirals in the outer disk being induced by the passage of some external perturber. However, that is not concerned. And so I don't have too much time left, but in brief, I remind you of the argument I mentioned from Elise right forward, that if you know the galactic potential, which of course we don't, you could unwind the phase spiral and learn about the timing of whatever perturbation has caused these things to start wrapping up. And so we can take Elise's algorithm and we can apply it to the phase spirals from Gaia DR3 and make measurements of the time that the interaction would have happened if this model is correct. So here we have, again, split by angular momentum or azimuthal, angular momentum or guiding radius, and azimuthal phase angle on the y-axis. And what we're really measuring here is the windedness of the spiral. And we're confident that we're quantifying the windiness quite well. If you use the simple model to go to time, we find a range of perturbation times from about 300 million years to about a gigayear. However, this is heavily model dependent, and all the stuff that I mentioned before, self-gravity, other effects, et cetera, can make this, the times not be correct, but the pattern appears to be robust. And there's also similar structure in the phase of these spirals. And the question here becomes, so you have this range of times, or the range of windednesses that you found. Is this from multiple events, or is this from like complex morphology of how these like wind up? And we haven't really solved that yet. However, independent estimates find essentially similar patterns. We have, again, this is our same grid here. We have angular momentum versus time found by Teresa and Toya using entirely different spiral unwinding time measurement-y code. And we have here on the right from Nej Frankel and Scott Ryan. Another version of it, you have age here versus angular momentum The nice thing from Nej's paper, she also quantified the amplitude of these phase spirals. And we see basically the same structure. So whatever it is we're measuring, it's nice to get the same structure out from 3 independent algorithms. You have this spike of high WARM, it means high time, thing kind of just outside the solar angular momentum. You have lower times inferred slightly inside, and globally a trend upwards. Note that we count hours off at 1,800, so we're missing the left half of the plots on both of these. That's because that enters the area where the 1 and 2 arm phase spirals overlap, and we got very high errors in our fits, we just sliced it off. However, if you go through that area where they overlap to the area where you just have clean 2 arm phase spirals, we recover a very, very low time. I believe from talking to Nej, that's the same that she found, but I don't have the plot. And so that's what I've mostly ignored so far, is what's actually making these phase spirals. We know how to measure them, we can map them, we can model them, but what actually causes them? Well, one of the leading contenders at the first time, when we first discovered it, was the Sagittarius dwarf galaxy. We know we have this dwarf that's merging into the Milky Way. It's been doing it for giga years. Myself, Teresa and Toya, Shrev on the board, Jocelyn Hawthorne have all run simulations of this. The difficulty is the present day mass of the Sagittarius remnant is pretty light. So 4 times 10 to the 8 solar masses, and that's not enough to do what we see with this. However, of course, it will have been losing mass for its previous pericenters, so it's possible there's a way to reconcile recent mass loss with degree of distortion. But no one's managed to do that, I'll say. Other options, are there any other recent current dwarfs? Of course, we have the Magellanic Clouds, but they're still on the first infall. It's not time for the phase spirals to wrap up. Magellanic Clouds should eventually make beautiful phase spirals across the Milky Way. We'll all be long gone. And other dwarfs, the 2 recent. Van Bannock has a nice paper that looks at the effects and rules out other things. Other options, collective bar. Sergei Kopeskov showed if the bar buckles, it creates a vertical disturbance that creates 1 arm phase spirals. And then myself, my bar in the model I showed you does not buckle. It grows slowly and resonantly and also makes spiral arms. So between them, the combination of the resonant growth or spiral structure, you can reproduce these. Scott Germain had the recent papers showing a series of smaller perturbers, such as dark matter subhalos, can also generate these phase spirals through, instead of one large perturbation, a series of lots of smaller ones. And Robert Grant showed that actually the Milky Way dark matter halo response can be enough to perturb the disk vertically to the degree that you see. So if you have an older satellite come in, make the halo significantly triaxial and out of equilibrium, then the halo effect on the disk is actually dominant, and that's what causes it all to wind up. And then also in the other direction, Scott's paper on GMCs can actually cause them to disappear sooner through action diffusion, through interaction with the giant Magellanic clouds. So given all that, what's the answer? What's actually making these phase spirals? And yeah, we don't know. I leave you instead with a mystery for today, but you have many groups working on it. So I think we should be able to come to some kind of consensus over the next few years, but at the moment it's still fairly fresh. Yeah, and that is the end for me. Thanks to all those collaborators who work I featured. I will leave up the summaries and take more questions.
Thank you, Jason. I think we have about 10 minutes for questions.
Yeah, so we go back to the time estimation of the impact. Sorry, the next one. Is it wonder how should we interpret these different age? Does it mean that if you pick a particular part of the Milky Way, then you expect like the impact is at some time, and if you choose another region, then that means it is another time. So that shows that these like single impact is scenario is not necessarily stable.
So this is the question that we are discussing at the moment. I think actually, this is something I'm interested to talk to more to Scott about while I'm here. But we have, if you have a long, slow interaction where the satellite like loops under the disk, the time when the stars at different parts of the galaxy experience the perturbation, the maximum perturbation, and start to wind is different. So you can create these kind of stripes with different timing from just a single interaction. But if you have one very incredibly rapid passage, that's not so much the case. I have somewhere in the bonus slides this picture. So this is from a test particle model from Elise that shows if you have this satellite that goes by and you measure all the phase spirals of the present day, and then you wind all those volumes back to where they were when the satellite crossed, which is not quite fair because the crossing time is slightly different, then you get close to a dipole in the times that are inferred. This isn't that big a difference. It's like 880 down to 820, so it's still within 100 million years, which is smaller than the range we see in the Gaia data. But the length of time spent doing the crossing and the mass of the satellite changes how different you can get. And then when these features all start to wind up, because the inner galaxy rotates faster than the outer galaxy, they can start to cross and leave bands of different phase spirals. So you can do it with a single perturbation to make different times. I'm not saying that's the right answer, but it doesn't rule it out.
Okay, so then I also wonder, so it seems that like with one spiral, basically you probably only have two things to constrain, right? One is like you have the single arm and the double arm strands, basically probably also have the phase of it. Right? So from one spiral you can constrain basically 4 numbers.
Yeah.
And now you have many different patches.
Yeah.
So what would you say about the degree of freedom of models you can constrain, like given the current guide? Because like you still have noise, right? So effectively you don't have infinite number of degree of freedom.
It's a good question. I don't know the actual answer to that, but if anything, we've given ourselves too much room to fit things with
because like for one passage or two passage, I suppose don't have many degree of freedom, but given the data, I have a lot of things to constrain. So basically, I have to say very strongly like whether the data is consistent with some model or not.
Yeah, you can certainly check consistency against like the simple models. I think the problem is that this one, basically all of this is going on, right? We have a Sagittarius, we have other dwarfs that are affected minimum, we have a galactic var, we have spiral structure, probably depending on who you talk to, probably have dark matter subhalos depending on your preferred theory of dark matter. Again, that dark matter halo probably responds somehow, and yes, we also have GNCs. So the question is one of these things dominant? In which case we can probably unwind and get the answer. But it could also be a really complex combination of all of this stuff because the galaxy does have all of these things. And then how you determine it, I don't know. Yeah.
Actually, ask a follow-up question on that. If you can go back to the slide of the time panel.
All right.
So presumably you're showing here each pixel here is a single highest likelihood time for unwinding.
That's
But
right.
in theory, you've got multiple patterns, and you could certainly have a 2-armed and a 1-armed spiral superposed. Is there any way you can decompose it to say there's one big global thing that kind of spreads through with a certain time, and there are local things that have a different time scale?
So that's actually what we're trying to do at the moment. I haven't put it in here because it's still too early days. It's Kian's project, if you know that, but for other people, we are trying to take those individual phase spirals and decompose them into the different modes using various basis function expansions of that space, and then correlate that both pull apart the different modes in the same spirals, but also correlate it to global spiral patterns. Currently, his results look really cool and kind of complicated. So yeah, it seems to be working, but we don't have any answers out of it yet.
So early on in the talk, you showed those plots of azimuthal velocity as a function of radius with these nearly linear features in it. Is there a simple explanation for why all of these effects produce nearly linear features?
So the understanding that I think we have, and I've seen written in a bunch of papers, is that resonances should make those features along lines of constant angular momentum, and phase mixing should make them along lines of constant energy. And that's what I've been told repeatedly by many people. But in practice, when you do simulations that contain both, they all get distorted enough that you can't quite tell whether they are following said angular momentum or energy. But it's one of those two. That's what they should arise from. People have tried to measure it, but when you're at the version of, so right back. Shows on do when you have this kind of distance in the Gaia data at the moment, it's not entirely clear whether this straight line here is truly a straight line, which would imply energy and phase mixing, or whether it is just the locally flat part of a curve, because we don't have enough fidelity to see whether it will later follow a line of constant angular momentum as you go out further into the disk. People do try to measure that. And so people have made a distinction between which could be resonant and phase mixing, depending on whether they follow constant energy or angular momentum. But I always like to caution for this, because when you have bars and spirals interacting, it's actually quite hard to measure. Like in any one frozen moment in time, some lines can look like they follow lines of constant angular momentum or constant energy, whereas in fact, given another 10 million years, the shape of this feature has changed from the interaction of the bar and spiral, fortunately.
The slope of the lines cannot tell you whether it's constant energy or what's the meaning of the slope.
Yeah, it should do. That's what it should tell you. The problem is when you have a clean galaxy with not much else going on, like this instance, you can measure these features. This isn't density actually, so this is slightly misleading because the density ridge follows a slightly curved line of constant angular momentum just on the top edge of this blue bit here, and that you can measure as firstly you can tell it's a resonance. You can tell the order of the resonance by how it moves azimuthally. You can tell the pattern speed of the bar by where it occurs in the space. You can tell the amplitude of the bar from how strong a feature it creates. However, as soon as you have a more complicated space, you don't know what you're measuring. You can still measure it. You just might be getting the wrong things.
I'm trying to understand what would be the simplest physical model that will give you the basic structure of the spiral. If I were to grab a self-rotating fluid, allow me for a second, and I do a local analysis, and I do, I impose some forcing in the vertical direction, will I get the basic structure of the spiral right or not? And if not, what is that it's getting wrong?
Again, honestly, I don't know exactly how your model would respond to it. In this instance, anything, if your self-gravitating fluid would behave roughly as like the simple harmonic oscillator that mixes back towards equilibrium, then yeah, you'll get a phase spiral. If you're doing constant forcing, I suspect you'd get something that's more standing, but I don't know. It's not quite my.
Because if I remember correctly, you do get, there is a way to get bending waves and breathing modes in a disk, right?
Oh yeah, we can do that.
And just, offering the question because it would be useful to have a very simple model that would get actually a spiral. I mean, you have some, sketches and cartoons, but
yeah. So there's the student we were working with from the Dynamics Summer School, the CCA, Uropan Banek, has done a lot more of the simple analytical models of how the spirals form and evolve. So I would direct you to his papers if you want to see that. But it's a good point, actually. I would do well to take some of his animations to show how they form, because he's done that quite nicely.
All right, so thank you, Jason, once more.